You move your mouse, double-click to open a heavy application, and nothing. The cursor turns into a spinning wheel, and your system stops completely. That split second between an application launching instantly and a total system freeze is decided by a sequence of physical events happening right inside your computer case. The system unit functions as a physical ecosystem, a highly organized arrangement of electronic parts that translate electrical pulses into the software we use every day. At the center of this environment is the system board, or motherboard. It acts as the grand electronic highway, providing the data paths that physically connect every single component together. Every performance lag or system crash corresponds to a specific failure point on this board. Mapping these pathways allows you to diagnose hardware failure and upgrade parts with surgical precision. Before you even click that heavy application, the computer has to wake up. This tiny BIOS chip holds permanent read-only memory. Powered by a CMOS battery, it provides the essential firmware instructions required just to turn the machine on. Once it's running, your application command goes straight to the microprocessor. This metallic chip contains the actual brains of the operation, the CPU. Inside that chip, the labor is strictly divided. A control unit acts as a manager, coordinating the overall plan, while the arithmetic logic unit crunches the massive mathematical operations required to run the code. To handle heavy workloads without crashing, modern machines place multiple CPUs on a single chip. These multi-core processors operate exactly like a kitchen with multiple chefs, executing entirely separate recipes at the exact same time. But those chefs need a counter to prep the food. This is a stick of random access memory. RAM is the temporary physical workspace holding the active files for whatever application you're currently running. If you open up too many browser tabs and heavy programs at once, that physical workspace gets entirely filled up. To prevent an immediate crash, the operating system triggers virtual memory. It slices up large programs and temporarily stores them on your secondary hard drive, only swapping them back into RAM when you specifically need them. Between the main RAM and the CPU, there is also cache memory, an ultra-fast holding area that keeps your most frequently used instructions ready for immediate access. You could buy the fastest processor on the market, but if your RAM workbench is too small, the system will choke. The processor physically cannot process instructions efficiently without enough active memory to lay out the parts. Computing requires moving the calculated data out of the CPU and RAM and physically transporting it across the motherboard. The data travels on bus lines, which you can see here as gold-copper traces branching outward from the processing chip. Bus width limits data movement. Wider buses handle more traffic simultaneously, acting like adding lanes to a congested highway. Looking at this diagram of a modern architecture, you can see how system builders have optimized this flow. Thick PCIe and memory bus pathways directly link the CPU to the memory and the GPU, bypassing potential traffic jams entirely. Eventually, that data reaches the edge of the system board and hits an expansion card, which plugs directly into a bus slot to expand what the computer can do. As shown by the graphics card in this layout, dedicated hardware with its own cooling fan takes raw data and turns it into complex 3D animations. Lower down, a sound card translates data into audio signals. Finally, those expansion cards push the completed signals out through physical ports on the back of your machine, like HDMI, VGA, or USB, delivering them straight to your monitor and external devices. A loading screen is a literal physical assembly line. Raw data gets assembled on the RAM workbench, processed by the CPU, shipped down the bus traces, translated by an expansion card, and finally pushed out to your screen. From the moment you double-clicked to the moment the application loaded, or froze, the system unit executed billions of these physical transfers. Because it is a physical assembly line, a computer system is only ever as fast as its slowest component. If you are trying to play a game and the 3D rendering stutters into a slideshow, the bottleneck is most likely an underpowered graphics card struggling to translate the data. If your display is fine, but simply having 3 applications open causes your entire system to lock up, your processor is starving because you've run out of RAM. Once you map the pathways inside the system unit, you stop guessing why a computer is slow. You look inside, find the bottleneck, and upgrade exactly what is holding the assembly line back. Take a look at your own daily workflow. What specific hardware component is causing your computer to bottleneck right now? Let us know in the comments below.